Hey everyone, and welcome. Today, we're going to pull back the curtain on a subject that, honestly, powers pretty much every piece of modern tech you use. We're taking a peek inside a university course, ENG 311, to really get a handle on the fundamentals of digital signal processing. So, let's just dive right in.
So to kick things off, let me ask you a question. Think about streaming your favorite song, making a super clear phone call, or even looking at something like an MRI scan. I mean, on the surface, they seem totally unrelated, right? But there's an invisible thread that connects every single one of them. Any guesses what it is?
Well, the answer is they're all signals, but more importantly, they are all cleaned up, refined, and made useful by this amazing field called digital signal processing, or, DSP for short. It is literally the hidden engine that makes our digital world tick.
So what exactly is DSP? Well, if we look at the official course description, it's the field that deals with how we analyze and design ways to process signals using digital tools, like computers. Basically, it's all about taking a signal from the real world, like sound or an image, turning it into a string of numbers, and then using some clever math to improve it, change it, or pull out crucial information.
All right, to really wrap our heads around what DSP is all about, we got to start with the basics. We need to learn its language and get familiar with the tools in its toolkit. So let's break down the core concepts you'd run into right at the beginning of a course like this.
First up is the signal itself. Now, out in the real world, things like sound are continuous waves. They're smooth and unbroken. But computers, well, they don't really do smooth. They think in numbers. So what we do is we sample that wave. We take thousands of little snapshots every single second. This turns the smooth wave into a sequence of numbers, creating what's called a discrete time signal. It's just like a movie, which isn't actually smooth motion, right? It's just a series of still photos shown really, really fast.
Okay, so once you have that digital signal, you need a system to process it. And the gold standard here is something called an LTI system. That stands for linear time invariant. Now, the name sounds kind of technical, but the idea behind it is actually super simple. It's all about being predictable. Linear just means that if you double the input signal, you get double the output. No weird surprises. And time invariant means the system works the exact same way today as it will a year from now. That rock-solid predictability is what makes all our tech so reliable.
So, we've got our signal, that stream of numbers, and we've got our system, our reliable processor. But how do engineers actually look inside that system to figure out what it's doing? Or how do they uncover the hidden details buried in the signal? How do they make sense of it all?
Well, they use two incredibly powerful mathematical lenses. The Z-transform is kind of like an X-ray for the system. It lets you peer inside, see its internal structure, and figure out if it's stable, which is just a fancy way of saying it won't spiral out of control. Then you've got the Fourier transform. This one is for the signal itself, and the best analogy is a prism. You know how a prism takes white light and splits it into all the colors of the rainbow? The Fourier transform does that for signals, breaking a complex sound down into all the simple frequencies that make it up.
So, with those powerful tools in our back pocket, we can move on to the main event, really the heart of DSP, designing digital filters. This is where all that theory gets put into practice to solve actual real-world problems.
So, what is a filter, really? Well, at its core, it's a system that's designed to do one thing: clean up a signal. It can get rid of unwanted stuff, like the annoying hiss on an old audio recording. Or it can isolate the specific parts of the signal you actually care about, like boosting the bass in a song while leaving everything else alone.
And when you're designing these filters, there are two main flavors. You've got FIR filters, which are pretty straightforward. Their output is just based on the current input and a few of the ones that came right before it. Think of it like a simple moving average. But then you have IIR filters. These guys are a bit more clever. They use a feedback loop, so they don't just look at past inputs, they also look at their own past outputs. This makes them super powerful and efficient. But you have to be careful, because that feedback loop means you have to design them just right to make sure they stay stable.
So that's the whirlwind tour of the core theory. But how would you actually go about learning all of this in a course like ENG 311? Let's take a quick look at the student roadmap.
Okay, first up, let's see how you're graded. You've got a couple of class tests, a lab test, some quizzes, but whoa, your eye goes right to the bottom line, doesn't it? The final examination is worth a massive 70% of the total grade. That tells you something really important. The goal here isn't just to memorize facts, it's to build a deep, comprehensive understanding of the whole subject.
And yeah, this chart really drives that point home. It's so clear visually. While all the other coursework adds up to a solid 30%,
That final exam is absolutely the main event, making up more than 2/3 of the final score.
The way the course is structured makes a ton of sense too. It builds on itself. You start with the foundations we just talked about, signals, systems, and those transforms. Then, you move into deeper analysis and start looking at how filters are structured. And finally, you get to the really fun part in Study Unit 3, the design phase, where you learn the actual techniques to create your own custom filters from the ground up.
All right, let's zoom back out, because this stuff isn't just abstract theory for an exam. This knowledge translates directly into practical, hands-on skills that are actually in really high demand out in the world.
And the course itself really emphasizes this. I mean, check out this quote from the guide. It's not about just sitting there with equations on a blackboard. Students actually get their hands dirty with industry-standard tools like MATLAB. It's that direct link between the theory and the real-world application that makes this knowledge so valuable.
So what skills do you actually walk away with? Well, as you can see, it's way more than just theory. It's about doing DSP. You learn how to actually implement filters, analyze signals using professional software, and even work with the real hardware, the special processors that run all these algorithms inside our phones and gadgets every single day.
So when you boil it all down, that's really the big takeaway here. Digital signal processing is that essential and, yeah, often totally invisible bridge. It takes the elegant, abstract world of mathematics and transforms it into the tangible, functioning technology we all rely on every single day.
So I'll just leave you with this one thought. Now that you've had a little peek behind the curtain, now that you know the basic building blocks, from sampling signals to designing filters, what signals out there in your own world are you going to see, or maybe what are you going to hear, just a little bit differently?